Good afternoon from Dhaka, Bangladesh. I'm Altaf Hussain, and this is the 22nd lecture on lecture series on X-ray crystallography and solid-state chemistry. We will discuss structures of solids. Well, I showed in the very beginning of the lecture series that I'm taking a syllabus of 2 credit of 8 semester of public universities of Bangladesh, where X-ray crystallography and solid-state chemistry being taught. This syllabus content was up 7 chapters, and we are now in the last chapter of the syllabus content. And the last chapter is structure of solid, how we describe these structures, various types of crystal structure, and that's what we will start describing, and probably that will take 3-4 lectures, maybe 5 lectures, and then we finish this X-ray crystallography and structure of solids as per the syllabus of public universities of Bangladesh for 8th semester undergraduate. Okay, in the very beginning, I said which are the books I am following for this whole content, and specifically for structure of solids, I follow this book, Crystals and Crystal Structure by Richard J. Tilley, and then Solid-State Chemistry and Its Application, Anthony R. West, Inorganic Solids, D.M. Adams. These are the books I follow, but there are many other textbooks also one can follow. Okay, about description of crystal structure, what we do, there are various ways to describe crystal structure. The common one, very common one, is when we refer a crystal structure, we refer the unit cell. That means we say size, shape of the cell, and the position of atoms, which we call atomic coordinates inside the cell. But this description is not sufficient to reveal the picture of structure looks like in 3 dimensions. We can add here that, let's say we take a example, a sodium chloride structure, and its unit cell is about 5.34 angstrom. So angstrom is 10 to the power minus 10 meter, you see. So this is a tiny, tiny unit cell. So one cannot sufficiently reveal it if we only take the 3-dimensional unit cell. Therefore, what we do, we take several unit cells and consider their arrangement relative to each other and find the coordination number at interatomic distance, types of bonding, etc. And that way of describing of structure, there are visual structures, there are different ways we describe the structure, and the most common one, close packing and also space filling polyhedra. How a structure could be defined as close packing way or space filling polyhedra. That is the most common tool. But we have to remember that types of structure, all types of structure cannot be described only by close packing or only by space filling polyhedra. Both methods have got their limitations. Therefore, the 2 methods are used to define the structure visually, how to visualize it. Well, there are several textbooks where models of structure are being described, as well as there are software packages which can be downloaded, and in many cases it's free of charge. So there we can see the structure expanded, rotated, change the color, and key structural features highlighted, etc. We can play with it in the structure to understand it. Okay, now we go to the business, that is metallic, ionic, and covalent molecular structure, which we can describe with the concept of close packing. What do you mean by concept of close packing? We are assuming that we have spheres, equal size of spheres, and then we describe it three-dimensional arrangement. And we have to remember that we have to have close packing so that a sphere is touched by its surrounding spheres. And that what is a main concept by close packing, that we should not have void. We should see the all spheres are touched by its surrounding spheres. For example, here we are taking one, you see, that this is a layer of sphere. And if we take, this is our x direction, this is z direction, this is y direction. And this is what we call the three axial direction, let's say. In three axial direction, all the solid spheres are touched with each other. So this one is the sphere. Let's say this is A, and then we have surrounded by these, there are 6 spheres. So this A has a coordination number of 6. Go to this figure, what you see that this possibilities of arranging spheres, there are voids. Here is a void, here is a void, here is a void. So if we take crystallographic access of this arrangement, we see there are voids which is not filled. So that is not a perfect close packing arrangement. This is what a perfect close packing arrangement is. Okay, then we go by regular close packing. Now we have to see that, you see, this close packing has, this one has a coordination number 4, you see. So close packing, which has got coordination number 6, we are considering this, that is, it is having a maximum density. Okay, so this arrangement here, this arrangement, you can see that there are voids. You see, here is a void P in this, here is P, and there are also another void R. Here is R, and this is what we have to take into consideration for having close packing arrangement. Okay, so there we say that there are 2 simple ways of close packing. One we call hexagonal close pack, that is HCP, another called cubic close pack, that is CCP structures. Okay, now how do we describe an hexagonal close packing or a cubic close packing? We go for that then. Okay, if we do remember that most efficient way of close packing is A and B to be in contact with each other in follow, and then we have hollow between 3 spheres in each other layer. We mentioned in the earlier slide that P layer, P hollow or R. Now this is what we are taking then. So if we have a close packing arrangement, let's say this green spheres, and then we take either P or R, that what is a void, and then place another sphere in it. Then we can see that we have arrangement like A and B. An arrangement like A and B. Then if we take 3-dimensional, what would be the next one then? Next layer, what would be the next layer? So if we go on, we will see that we have either S or T voids in this. This is S or this is a T voids. And if we put one of this void, another layer of closed spheres, what you can see that there is 2 options. Either it is the first layer, A layer, or the another layer, that is, we discuss it in the next type of close packing. If it is just on top of the first layer, then we have a sequence like this, AB, AB, AB. And this sequence, if we continue like this in 3-dimensional, that is perpendicular to this close packing layer, then we see this type of close packing we call the hexagonal close packing. Okay, then what is the cubic close packing? Then we go for that. Well, you see, now we have an arrangement where you can see that either it will take T of the figure 2 and then place a sphere layer. We will see that it is not exactly like A. It's another arrangement. This is one is C then. So we can show you here this layer is C, this layer is B, and this layer is A, and continue like this. Then the fourth layer, we will see there is a possibilities of the fourth layer, which is again as like layer A. So the arrangement becomes now ABC, 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 and we call that the cubic close packing. So the other one in the last slide showed how a hexagonal close packing we can do, and here we can see the cubic close packing. Mind it that we can take spheres of equal size and develop this model, and we can see that the arrangement we are talking, there are only two types of arrangement we can have. One is ABC, AB, 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 which is hexagonal, and another is ABC, 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 which is cubic close packing. We'll come to it later in later slides, why you call it cubic close packing, why you call it hexagonal close packing. We'll see that here symmetry elements comes into the picture, and therefore we call this hexagonal and cubic close packing. So we have, now then, do we have further complex sequence? That means if we have A, B, C, and other layer. Yes, we do have this sort of arrangement, ABC, ACB, or ABC, AC, this sort of arrangement. And this is rather complex, and we do have some crystals arranging like this. So this phenomena is called polytypism. So phenomena polytypism that we have, but these are seldom seen in real structure. We see this sort of arrangement, only hexagonal close packing and cubic close packing more often. Okay, so we do have also a non-close packing structure. An example, let's say example in alpha iron, and that is what is body-centered cubic structure. We'll see that there are space filling, the hexagonal and cubic close packing. There we will see that we'll calculate it, find out that 74% space being filled. But in body center structure, it's about 68%. We will come to it in later slides. Okay, now we go for next slide. Now, okay. Now, relationship between close-packed structure and face-center structure. That's what we are describing a little bit here. We know very well a face-centered cubic lattice. That means we will get filled, if it is a unit cell, we fill all the corner by the sphere and also the center of the face being filled. And that's what we call face-centered cubic lattice, if it is having cubic symmetry. Then this is how we see, and therefore we know very well that one of the corner sphere is shared by 8 other unit cells. So all these 8 corners here, being shared by 8 other units. Therefore, only one atom here we get the one sphere. And then we have also 3 atoms. If we take this sphere or atoms in the face center, that will be shared by another face of the unit, another unit cell. Therefore, this we will get 3 atoms. So any face centered unit cell, we will have 4 spheres. That is a 4 sphere. And that 4 sphere, we can see that these can be also described as A, B, C, etc. So if we take this one as a layer of sphere, this one then B, and this this is B, and this is C, and therefore this again comes here, it will be. So this is how we describe, see the relationship between cubic closed-packed and face-centered cubic lattice. You can see that if we take this one direction, this is the fold, this is the atom, this we are showing it, this is atom, this is the A layer, and this is the B layer, and this is another C layer, and then again A layer. So it is A, B, C, and therefore we call this a cubic closed-packed structure. And this is the same here we are showing in another direction. This one, that is, if we take this is A, and then this will be B, and this will be C. We are looking at in another direction, the same. So 4 different orientation of closed packing shown in this figure too. Okay, so here we see the different type of orientation, how it goes, and rotated slightly by these pictures. We are describing the face-centered cubic lattice and the relation between a cubic closed-packed lattice. So that now we have also hexagonal unit cell or hexagonal closed packing. So here is a figure where we can see the hexagonal arrangement of this. We'll see that if we arrange it like this, we will have a threefold rotation axis as well as a sixfold rotation axis. We'll get a C-glide plane here to describe all this and getting the atomic position inside the cell. So that is what is our main aim, to describe this hexagonal unit cell and hexagonal closed packing, as well as how the atomic coordinates we can describe giving these pictures. So if this one is showing the glide planes, C glides, and there are the silica 1, then position 2, 3, 4, and 5, and 6. And this is created due to the C glide plane, this C glide plane. And then we see also the atomic heights of the C glide planes. And there we are showing how the threefold rotation axis arises due to this hexagonal arrangement, and also six-fold screw axis is having this arrangement. This is how we show the manifold main symmetry elements, as well as the close packing related to hexagonal close packing. Okay, with this slide, and next slide we will probably take, I said in the beginning, the density of close packed structure. We will see how we calculate the density of close packed structure, and we come to this value, that is 74.05% total volume occupied by the spheres, both in hexagonal close packing and close packing, a cubic close packing. We will have this value. You can calculate this using this figure, and if we take the radius of the sphere is r, then we can find out how we can get this value, that 74% volume, total volume is occupied by spheres. And this is what is the calculation scheme. We can find it out here, 0.740. Right? Similar result we can obtain for, as I said, hexagonal unit cell also. And then we said that if we remember that the body-centered cubic, in that case, the total volume is only 68% is being filled. Now, as we said, 74%. Then what are the rest? The rests are voids, which we will discuss in the next lecture, how the borders are created and what are the type of borders we do have in close packing. And then understanding this, we can describe different structure of metals, alloys, and then ionic and covalent compounds with the help of this closed spec structure. That is our intention to describe the structure with this concept and see it more visually about the structure. That's what is the aim of this lecture. I hope that in the next lecture we will talk about borders and then finally take examples which one belongs to which type of closed packing. I hope I could explain it a little bit more, and you have a basic concept now about closed packing, and we will take examples in the next lecture. Thank you very much for your kind patience and here. Thank you all. We hope that in the next lecture we could finish closed packing type of structure description. Thank you.